Hello, everybody. Welcome to the monthly fourth seminar. And my name is Kyusei Tsuno, a research scientist of the force. And today I'll be leading this seminar because Dr. Kara Bragman is out of the campus right now. So before starting the seminar, I will briefly talk about force update. Then we have several SNS channels like YouTube. On the YouTube, we this seminar is actually recorded, and at some point we'll post this seminar. And we have X and LinkedIn and Instagram SNS channels. So please subscribe it. And next month, Professor Azuma Bodeba will give a talk, and on May 2nd, Professor Damambia Greval will give a talk. Okay, so we are very glad that we invite Professor Rebecca Fischer as an fourth seminar speaker today, and Rebecca received her bachelor from Northwestern University, and after that, she obtained the PhD in University of Chicago. Then she spent 2 years of the postdoc joint program of the between the Smithsonian National Museum, National History, and the University of California, Santa Cruz. Then she is a faculty member at the Harvard University from the 2017. And her background is probably mineral physics and geochemistry and planetary chemistry. And she's interested in the physical chemical property of the planetary core and the mantle materials. So today she will talk about a candidate of the light element and the element composition of the Earth's core. So yeah, Rebecca, you can start.
Okay. Um, Thank you for the introduction and thanks so much for having me. I'm going to be telling you a bit today about what we know about the light element composition of the Earth's core. This is going to be a bit of a whirlwind tour, so I want to start by saying that if you want more details on anything that I'm showing today, most of what I'm going to talk about comes from a new treatise on geochemistry chapter that I wrote with Bill McDonough. So you can find some more information there. And I want to just start by thanking Bill. Many people who gave us some really helpful feedback on this work, as well as funding from NSF and NASA. And I would like to preface this by saying that I'm not going to tell you the answer at the end. I would say that we still don't really know exactly what the core is made of. So this is going to be sort of an update, give you the kind of an overview of the state of constraints that we do have, so that hopefully we can see where we can best direct our efforts going forward to further narrow this down. So we've known for quite a long time now that the Earth's core is mostly made of metallic iron with about 5% nickel. What's interesting is what else is in the core. And this very famous tongue-in-cheek table from Birch 1952, he explains that when high-pressure scientists talk about the Earth's iron core, what we really mean is that it's an uncertain mixture of all the elements. And there is some truth to that. All of the elements should be in the core to some extent. It's just a question of their relative abundances. And so in this talk, I'm going to be focusing on the roughly 10% of so-called light elements. Today, I'm going to be specifically focusing on silicon, oxygen, sulfur, carbon, and hydrogen. And this figure shows just one example of the evidence we have for these light elements being in the core. We're going to come back to this figure in a few slides, but this is showing density as a function of pressure or depth within the Earth over the range of the Earth's core. So the gray region here is the density structure of the Earth's core from seismology. And you can see it's the density of pure iron is in the right ballpark to match the core, but the core is a bit less dense. And that's one way we know that these light elements are in there. And there's a wide variety of reasons why the light elements in the Earth's core are important. Just to give a few examples, they serve as a sort of thermometer. They tell us something about the thermal structure of the core. And that's because at the inner core boundary, where we have the solid inner core crystallizing out of the liquid outer core, the temperature should be near the liquidus temperature of the core alloy. The problem is that different light elements can significantly depress the melting point of pure iron by very different amounts. This probably outdated figure just shows some estimates of the eutectic melting point depression you get in each of these binary systems. Of course, it's more complicated in a more realistic multi-component system. But the idea is that there's uncertainty in the core temperature because we don't know what it's made of. And if we knew its composition, we would at least get this anchor point at the inner core boundary. That would tell us something about the thermal structure of the core and therefore the heat flow into the base of the mantle that's helping to drive things like mantle convection and plate tectonics eventually. These light elements also play a really important role in the generation of our magnetic field. That's a very important component of our planet's habitability. As the inner core is crystallizing, these elements are preferentially excluded from the inner core. So they they're released at the base of the outer core, and then they rise buoyantly, helping to drive outer core convection that gives rise to the dynamo. They also make up a significant enough fraction of the core that they are important to understanding the bulk composition of our planet, and therefore things like how it formed and what it's made of. In particular, some of these candidate light elements are volatile, meaning they evaporate and get lost easily. So things like sulfur, carbon, hydrogen. So if we better understood how much of them was in the core, we would know how much of them is in our planet, and it might help us better understand processes related to volatile depletion. And we know that other rocky planets have light elements in their cores too. The Earth is the planet where we have the best data. So if we can better understand the composition of our own core, we would be able to make some comparisons to those of other planets. And there's a lot of different ways we can approach the question of what the core is made of. These are the ones I'm going to go through today. There's sort of cosmochemical, geochemical arguments for what the bulk Earth's composition should be. There's physical properties of the core, things like its density, seismic velocities, and phase relations that we can compare to mineral physics data to see what best matches the core's properties. Or we can look at the process of core formation. So like metal silicate reactions, how much of each element should have gone into the core as it was forming. So I'm going to start by talking about these sort of cosmochemical constraints. Just go through them very briefly, because this was more Bill McDonough's area of expertise. But the logic behind this is that if we know something about the composition of the bulk Earth, and we know the composition of the bulk silicate Earth, or BSE, which is the mantle plus crust, so we have samples of it, we can subtract the BSE from the bulk Earth, and the difference between them is what's in the core. We can get some insight into the bulk Earth's composition by looking at primitive meteorites, like this one. And that works well for more refractory elements, the ones that don't evaporate so easily. For volatile elements, it's a bit more complicated, as you'll see in a minute. So one example of this comes from looking at the magnesium to silicon ratio. So here I'm showing the value for the BSE. as compared to carbonaceous meteorites in blue and non-carbonaceous meteorites in red. And what you can see is that the magnesium silicon ratio of the BSE is higher than any of these meteorites that might have been its building blocks. And if the core contained like at least a few weight percent silicon in it, then the bulk Earth would plot to the left of the BSE. It would be more in line with what we think the Earth is sort of made of. It would reconcile the magnesium silicon ratio with these different meteorites. And this is not a new idea. It goes back at least a few decades. For example, Allegra et al. In 1995 argued that this is a sign of something like 7 weight percent silicon in the core. We can also do this for moderately volatile elements. So this is a figure from Wood et al. 2019. It's showing the abundance of all the different elements in the bulk silicate Earth relative to CI chondrites. And they are plotted as a function of their 50% condensation temperature. So on the right is things that are more refractory, and on the left, things that are more volatile. And if you first look at the blue points, those are the lithophiles, the things that are mostly or entirely found in the silicate portion of the Earth. So that what's in the BSE should reflect what's in the bulk Earth for these elements. They define this sort of gray shaded trend in the background, the volatile depletion trend of the Earth. If we're looking at siderophile elements that can be significantly sequestrated in the core in red and green, they all plot below this trend because we're just looking at their BSE abundances here. And so we can use this to look at how much sulfur should be in the core. So there's some depletion of sulfur in the Earth relative to chondrites due to its volatility. So the bulk Earth's sulfur abundance should plot on or near this trend. But when we look at how much sulfur is in the BSE, it's this red point way down here. The difference between that point and this gray trend is depletion due to core formation. So the amount of sulfur that's hidden in the Earth's core that we can't see should bring sulfur up onto this trend for the bulk Earth. And if you look at that sort of difference, that can be accounted for by the presence of something like 1.5 to 3.3 weight percent sulfur being in the Earth's core, depending on whether you're comparing the abundance to carbonaceous or non-carbonaceous meteorites. I should point out this kind of volatility argument is a lot harder to do for the highly volatiles, things like carbon, hydrogen, oxygen. They're so volatile that they don't necessarily sit on this trend, so it's a lot harder to estimate their core abundances this way. Okay, so those are a couple of the cosmochemical constraints we have on Earth's core composition. Now I'm going to talk about some of the mineral physics constraints. What sorts of compositions can best match the core's physical properties in terms of things like its density, seismic velocities, and phase relations. We're going to start by looking at the density. Okay, so here I'm showing density as a function of depth or pressure for the Earth's core. So this comes from these 4 different seismological models. So we're going from the core mantle boundary on the left, there's the inner core boundary, and on the right is the center of the Earth. So you can sort of rephrase the question of like, what is the core made of? And instead ask which iron alloys can best match the density that we see. So we need some data on the densities of iron alloys to compare to the seismologically determined density of the core. So to do this, we look to equations of state. So this is a thermodynamic framework that lets us relate pressure, temperature, and density, or equivalently molar volume, using material properties. And there's a number of ways you can determine the equation of state of something using different experimental or computational techniques. In this example, we used synchrotron X-ray diffraction with a laser-heated diamond anvil cell. So we had a tiny sample pressed between two diamonds to generate high pressures, used infrared lasers to heat it up. And while it was at those high pressures and temperatures, we did X-ray diffraction. And from those diffraction patterns, we could determine its density at all these different pressures and temperatures. So this is an example of what this looks like. Here I'm showing the molar volume of HCP alloy with 9 weight% silicon in it as a function of pressure. The symbols are data color-coded by temperature, and the dashed lines are the fitted equation of state. So with these equations of state, then we can calculate the density of these materials at any pressure and temperature that we're interested in. So we're going to start by doing this for pure iron. So this is the same kind of figure again. The gray shaded region is the core's density structure from seismology, encompassing those 4 studies I showed a couple slides ago. Now the red curves are calculated for equations of state of solid HCP iron, and the sort of blue and purple curves are from equations of state for liquid iron. In doing this calculation, you have to know something about the core's thermal structure. So these curves here are calculated assuming a potential temperature of 4,000 Kelvin at the core mantle boundary with an adiabatic temperature profile through the core. And if we compare the density of pure iron to that of the Earth's core, in the outer core, we find a density deficit of something like 7 to 9%. And in the inner core, something like 5 to 6%. Although you can get slightly different numbers depending on what you think the thermal structure of the core is like. And then we can do this for different iron light elements alloys. And so again, using silicon as an example. So in gray is the Earth's core density. This sort of pink shaded region is the density of solid iron. And then all of these thin colored curves are calculated from equations of state from a bunch of different studies looking at iron silicon alloys with different silicon contents. And if we sort of look at them all together, we find that on average, adding 1 weight% silicon to iron lowers its density by something like 0.1 grams per cubic centimeter. So if we want to match the density of the outer core at the core mantle boundary, it would take about 8 or 9 weight% silicon with iron to do that. So this is effectively an upper bound on the core's silicon content because there's going to be other light elements in the core, and so you'll have to have less silicon to compensate. And you can do the same thing with other kinds of compositions. So these are the same kind of calculation for oxygen, sulfur, carbon, and hydrogen in the core. And we can similarly calculate how much of each of these light elements you would need to add to iron to match the core's density. So that's something like 8 or 9 weight% silicon, 7 weight% oxygen, 10 to 15 weight% sulfur, 6 to 9 weight% carbon, 0.4 to 2 weight% hydrogen. And again, these are effectively upper bounds on the core abundances of each of these elements, because that's how much it would take to match the core's density with just that one element. I should also mention these equations of state we're using. Some of them are experimental, some are ab initio, some are combination, some are thermodynamic calculations. Some of them are on solids and some of them are on liquids. And in those cases, we compare them to the equations of state for solid versus liquid iron, respectively. But there's some huge caveats in doing an analysis like this. There's considerable uncertainties in the equations of state, in the density of the core, and in the temperature of the core. So we try to consider sort of a range for all of these things. Most of the equations of state I showed on previous slides are significantly extrapolated in pressure and temperature. That is why we often sort of focus the calculation on like how to match the density at the CMB, assuming there's no like thermal boundary layers there. We have a lot more experimental data on solids than we do on liquids, just limitations and the kinds of measurements we can make. which makes it harder to make comparisons to the outer core. There's certainly not no data on liquids. There's certainly some like shock data at these pressures, for example, which I am not going to go into today. So what we've done instead in cases where we have solid iron alloy densities, we compare them to the density of solid iron to estimate their effects on the density of iron and make the assumption that that will also apply to liquid iron in the outer core, which is certainly an assumption. And given the extrapolations in pressure and temperature, the densities that are being measured might not be on the same phase that would be stable in the inner core. There's generally less data on iron-hydrogen compounds due to mostly technical difficulties in studying those, and there's a lot more variation between studies. There's also not nearly as much data on multi-component systems, although again, there are some that I'm not gonna go into much today. And doing this type of analysis does not easily lead to a unique solution for what the composition of the core has to be. It instead gives us a sense of how much of each element you need to match the density by itself, and that's sort of an effective upper bound on their abundances. We can do the same kind of exercise looking at the core's seismic velocities, which I will go through a little quicker. So this figure is showing VP, the compressional wave velocity, versus depth or pressure from a bunch of different seismic models. And then the inset here is showing VS in the inner core. So we know something about the velocity structure of the core from seismology. And then we can compare it first to the velocities for pure iron. So these are so-called Birch's law plots showing velocity versus density with VP on the top panel and VS on the bottom panel. In both cases, the gray shaded regions are the range of velocities reported in these different seismic studies. The black curves are velocities for pure iron calculated along an adiabat at core conditions. And the colored lines are all isotherms for pure iron. And again, this is sort of a mixture of sort of ab initio thermodynamic calculations, experiments. There's lots of different techniques you can use to measure sound velocities. In this part of the talk, I'm going to mostly be pulling from ISX studies for measurements of VP and Enrich's study for measurements of VS, but there's a lot of other data out there. And what we can see from this kind of figure, like with the densities, iron has the velocity that's in the right ballpark to be in the core, but it's not an exact match. In particular, if we look at the inner core, it has a rather high Poisson's ratio, the Poisson's ratio being a measure of the VP to VS ratio. So in other words, the Earth's inner core has a high VP and a low VS compared to what we would expect for pure iron at the same conditions. We can make the same kind of plots for various iron light element binary materials. So now the black curve is for iron at 300 K, and all the colored lines are for different iron binary compounds also at 300 K from a bunch of different studies. And what we can see, at least at 300 K, that adding light elements to iron generally has the tendency of increasing VP and decreasing VS, which is the right direction to improve the match to the velocities of the Earth's core. But it's hard to put an exact number on it the way we could sort of with the density for a variety of reasons. There's uncertainties in the velocities of these alloys, in the velocity of the core, in the temperature of the core. Even more so than with the equations of state, most of these velocities are very significantly extrapolated in pressure to make this figure, kind of recklessly, sorry to the authors of these original studies. And most of the data that we have are at 300 K. Again, certainly not all of it, but much of the high temperature data we do have is at relatively modest temperatures relative to the core. So for some of these materials, we really don't know all that much about the thermal effects on their velocities. This also means we have much more data on solids than liquids, which again makes it difficult to compare the data directly to the outer core. And because of these large extrapolations, they're often not on the relevant phase to apply to the inner core. And again, there's less data on multi-component systems, although not none. And this kind of exercise also will probably not give us a unique solution to what the core's composition is, but it will certainly help us narrow it down as we continue to sort of push the techniques to get more data at higher pressures and temperatures. And then the other type of constraint we get from mineral physics is to look at the phase relations of the core alloy. So if we pretend for a moment that the core is just a binary alloy, just FeX, where X is some light element that has a eutectic behavior. Just for the sake of visualizing this, we can draw this sort of cartoon phase diagram in temperature composition space for this eutectic melting. There are two things that we know must be true about the phase relations of the core alloy. The first is that the core's bulk composition, shown by this red dashed line, has to be on the iron-rich side of the eutectic composition, which is this darker red square. We know that has to be true because that's how you crystallize an iron-rich solid, like we have as the inner core. If we were on the other side of the eutectic, what's crystallizing would be more rich in light elements. The other constraint we have on the core's phase relations is the density contrast at the inner core boundary. The density jump that we see there must be explained by the kind of difference you have between solid and liquid compositions, sort of integrated over time as the core is forming. Okay, so to start with this first constraint, we have to be on the iron-rich side of the eutectic. This is an example coming from the iron silicon system from a study by Ozawa et al. 2016. So again, this is a temperature composition phase diagram, like the sort of schematic one I just showed, only this one's based on actual data. And these red arrows point out the eutectic composition. So there it is at 50 GPa. By 120 GPa, it has shifted to lower silicon content. And this curve down here comes from the same study, sort of combining constraints from a bunch of previous studies shown by these arrows on what the eutectic composition in the iron silicon system, how it changes with pressure, shown by this gray arrow. So at least over this pressure range, up to about 150 GPa, the eutectic composition is just shifting more and more toward pure iron. And in particular, it is on the iron-rich side of the kind of silicon content we would need to match the core's density if the core was just an iron silicon alloy, shown by this red symbol. So if this trend continues to inner core boundary conditions, what this means is that silicon can't be the sole light element in the Earth's core because it's the core's composition would be on the wrong side of the eutectic and the iron silicon binary. Note, it's hard to extrapolate these things because you can have subsolidus phase changes that can suddenly change the eutectic composition. It's very, very hard to do these experiments at 330 GPa. So extrapolation is often necessary. But that does make everything I'm about to say something you should take with a grain of salt because we really need more high pressure data on this. But people have looked at a bunch of different binary and ternary systems to sort of ask this question of like, how does the eutectic composition evolve with pressure? Would the core's bulk composition be on the right side of the eutectic or not? So here's a few examples of systems where it seems like you might be on the correct side of the eutectic, although again, this often involves extrapolation. And here's some examples of a few binary and ternary systems where it seems like you'd be on the wrong side of the eutectic. They wouldn't work. And what you will notice is that all of the ones that seem like they could work have oxygen in them. So that suggests that there should be some non-trivial amount of oxygen in the Earth's core in order to be on the right side of the eutectic to be crystallizing an iron-rich inner core. Again, this requires significant extrapolations in most cases. There's also not a ton of data on many of these systems because these experiments are so difficult and labor intensive. Okay, and the other kind of constraint on the phase relations. The difference in composition between the solid and liquid has to account for the density difference between the inner and outer core at the inner core boundary. So this blue arrow here in the upper figure, this density jump at the ICB is what we're trying to explain. The figure on the bottom is a summary of a bunch of different estimates from seismology on what this density difference is at the inner core boundary. These studies use very different seismological methods. Some of them only give an upper bound shown with the arrows. Some techniques are a lot more sensitive to this property than others. I've just sort of plotted them all up here. You can see that they're all roughly in the ballpark of 4 to 7% increase in density at the inner core boundary. So for comparison, the change in density in iron when it melts at these kinds of pressures is something like 1 or 2%. That's the density difference you get just from changing from a solid to a liquid without any change in composition. So that accounts for part of this density difference, but not most of it. So we want to quantify each of these light elements' preference for solid versus liquid iron. We can do this using a partition coefficient D. So for example, if we're thinking about sulfur, the D for sulfur is just the mole fraction of sulfur in the solid divided by the mole fraction of sulfur in the liquid. You can do this with a variety of experimental or computational methods. This is an example from Mori et al. 2017. For example, you can use a diamond anvil cell, subject your sample to high pressures and temperatures to partially melt it, bring it back down, recover it. So here, this is an image of a cross-section through their recovered sample that was from 34 GPa and 1630 Kelvin. And then they did this X-ray mapping of the sample. So in the center here, where the laser was, is where it was melted. And you can see it's mostly this sort of yellowish greenish color. That's the map of sulfur. And the phase right on either side of the liquid is mostly red. That's where they detected iron. So in this example, there's much more sulfur going into the liquid than into the solid. So it exhibits a small value of D, something like 0.1. So that's meaning there's more sulfur would partition into the outer core. But D depends on a whole bunch of different variables. So this figure is from Sakai et al. 2023. I'm showing the partition coefficient of sulfur versus pressure. The black symbols and curves are for just the FES binary system. And you can see at low pressures, D tends to increase with pressure. There's perhaps a discontinuity here when the solid changes from FCC to HCP. Then it continues going up, and then somewhere around 200 GPa kind of flattens off and stays constant. But it's also affected by composition. So for example, the various colored symbols show different amounts of silicon in an iron silicon sulfur ternary. And in this case, it shows that adding silicon lowers the D of sulfur. So we know the core has some combination of light elements in it that together have some kind of intermediate value for their effective average D. In other words, D can't be zero because there's some light elements in the Earth's inner core. We can see that because the inner core is less dense than solid iron. But D also can't be 1, because that would mean the elements have no preference for solid versus liquid. And we know that's not true because they're based on density, there's more light elements in the outer core than in the inner core. So if we look at all of these candidate light elements, this is sort of a rough summary from a bunch of different studies looking at various binary and ternary systems involving these elements. And what you'll notice is that oxygen and carbon in blue have partition coefficients very close to 0. They partition very strongly into the liquid, too strongly to be able to explain the inner core's density, perhaps. On the other hand, silicon, sulfur, and hydrogen in red all have Ds close to 1, especially silicon, whose D can even be above 1. So they may not partition strongly enough into the liquid. So this suggests that the core probably has some oxygen and or carbon in it, and also some silicon, sulfur, and or hydrogen in it, to end up with a D somewhere in the middle that's going to be able to explain that density contrast. Although it's not trivial to convert from a density contrast to a composition, partly because it's a non-unique solution, but partly also we need to understand exactly how much each of these elements will affect the density at these conditions. Okay, so that was a quick overview of mineral physics constraints. Now in the last part of the talk, I'm going to show you some of the constraints we have coming from core formation and the metal silicate reactions that took place. So we study core formation because it set the initial composition of the core and also the BSE. This is a process that would have taken place as the Earth was accreting. These impacts would have generated a deep magma ocean on its surface, and molten metal and rock from these impactors reacted at high pressures and temperatures. So we can use this to sort of estimate what the composition of the core should be from its formation if we know something about these kinds of metal silicate reactions. And the key piece of information that we have here is the composition of the bulk silicate Earth, since this core formation process also shapes its composition. We know it has to come out matching what we see today. But as I will show you, the core composition you get from this depends a lot on model parameters. That is, it depends a lot on the details of how this process happened. But this is kind of a neat way to look at core composition because it gives you a constraint that is independent from the types of constraints I just described. So we can investigate the partitioning of elements between metal and silicate using high pressure temperature experiments. This has been done quite a lot in large volume presses, like the ones at Force. In my group, we do this using a laser heated diamond anvil cell to get to high pressures and temperatures. And other people are starting to do this using ab initio or other computational methods. Basically, you take a mixture of metal and silicate, bring it up to some high pressure and temperature, melt it, let them react for a minute, and then quench it to sort of freeze in that chemistry. And then we recover the samples to 1 bar. We polish or extract a piece of the sample using a focused ion beam. So we expose the hot part in the center where the reaction took place. And then you can use various different analytical techniques to measure the compositions of the metal and silicate that reacted. So this is, well, 3 images of a sample from one of our studies. On the left is a backscattered electron image with the microprobe, just so you can see the sort of morphology of the sample. It looks kind of like a mini Earth. It's got this metallic sphere in the middle, surrounded by a shell of molten silicate with some weird quench textures. And then these other 2 panels are the same sample that we analyzed using nanosims. These are maps of the oxygen and carbon abundances in them. So the sort of purple, pink, red colors are higher abundances of carbon or oxygen. So what you can sort of just qualitatively see, just looking at these images, Oxygen, of course, concentrates in the silicate, but there is a non-zero amount of oxygen in the metal. Similarly, carbon is always concentrated in the metal, but there's a non-zero amount in the silicate. And so we can quantify this preference for metal versus silicate, again, using a partition coefficient, this time defined slightly differently. So for example, the D for silicon is the mole fraction of silicon in the metal divided by the mole fraction of SiO2 in the silicate. And so this figure is some of the data that's out there for the partitioning of silicon. So I'm plotting the log of its partition coefficient minus this other term. That's to normalize out the effects of oxygen fugacity, plotted as a function of inverse temperature. So there's data from a wide range of pressures from a large number of previous studies. We often like to combine a bunch of data sets like this because each data point is very labor intensive, and different techniques are better at different pressure temperature ranges. So we can sort of pool the data together to get a better picture. And then parameterize how D can change with different variables, things like pressure, temperature, FO2, NBO over T, a measure of the silicate melt structure, composition of metallic and silicate melts, etc. And in this case, after sort of testing its dependence on these variables, we found that the partitioning of silicon can be described just in terms of temperature and FO2 here relative to the iron Weisstein buffer. And that's the line in this plot. So what you see is that silicon prefers to go into the silicate. This value is negative, which makes sense. That's what we call lithophile. But as you go to higher temperatures to the left, its partition coefficient increases, meaning it goes more into the metal at higher temperatures. To apply this to the Earth, we have to put this into some kind of model. So this is a core formation model. I'm going to show you results for 3 Earth analog planets that formed in N-body accretion simulations. We just use those simulations to get a sense of their mass evolution and the provenance of their impactors. We assume the impactors all have a chondritic composition in terms of refractory elements and allow for variable depletion of volatiles, in this case, carbon and sulfur in particular. And we assign each of these impactors an initial FO2 based on where in the solar system they started out. So a more reduced inner solar system, a more oxidized outer solar system. And then as they're accreted by the Earth, the FO2 of the Earth evolves self-consistently after Ruby et al. 2011. Every time the Earth experiences an impact, there's a core formation episode. This is assumed to take place at a fixed fraction of the core mantle boundary pressure at that time. So that pressure is always increasing and near the liquidus of the mantle at that pressure. We react all of the impactor's mantle with some of the impactor's core and some of the target's mantle in each step. And then that metal gets added to the Earth's core, sort of hidden away. That silicate gets mixed into the mantle, and we repeat this process with every impact. So this is a very complicated process that we're trying to simplify in a model like this, using a relatively small number of parameters shown here. So the bulk volatile abundances, initial FO2 distribution, the pressure at which the equilibration occurs, the temperature expressed as a deviation from the liquidus of Andra et al. 2011, and the amount of metal and silicate that react in each step, which expressed as K-core or M-sil, the mass of the silicate. And so I'm going to show you some results from a sort of thought experiment looking at the partitioning of silicon, oxygen, sulfur, and carbon. So here we explore a wide range of parameter space, making sure that we always approximately match the BSE composition in terms of iron oxide, nickel oxide, cobalt oxide, carbon, and sulfur. But what we want to see is what's the widest possible range of core compositions we can get from core formation alone, while always matching what we see in the BSE today. So I'm going to show you results from 3 different combinations of parameters that we found maximize the amount of silicon, oxygen, or sulfur in the Earth's core. So this is just showing how the bulk silicate Earth's nickel oxide in orange and cobalt oxide in blue evolve over time. So the three different panels are three sets of parameters. Within each panel, the solid dashed and dotted lines are three different Earth analog planets. The arrows are the observed values in the BSE. So despite using really different like model parameters for the conditions of core formation, these three cases all approximately match the observed composition of the BSE. However, they give very different light element compositions for the Earth's core. So here I'm showing silicon in purple by a factor of 10, oxygen in green, sulfur in red, and carbon in orange. You can get quite a lot of silicon in the core. You can sort of maximize sulfur, carbon, and all these different sort of combinations. We played around to see sort of what are the extreme cases, the highest and lowest amounts of each element, and came up with these approximate bounds. I will start by saying these bounds come just from this exercise of modeling core formation. They're not necessarily intended to be compatible with the other constraints I just discussed, like 12 weight percent silicon, for example, is too much to match the density. But it gives us some sense of the ranges that are allowed. So matching the bulk silicate Earth's composition does not necessarily give us very tight constraints on core composition, but different for different elements. So there's a wide range of silicon contents you can get in the core from core formation, and relatively speaking, a narrower range of oxygen if you're including self-consistent FO2 evolution. That comes from silicon and oxygen having an opposite dependence on FO2 during core formation. For sulfur and carbon, we can sort of only place upper bounds on their abundances by assuming they were delivered uniformly throughout accretion, since they tend to become less siderophile over time, and neglecting contributions from late accretion. That gives us these upper bounds, but if you wanted to put a lower bound on it, you'd have to look more closely at those processes. Also, not all combinations of light elements within these ranges are possible. For example, higher silicon tends to give you lower oxygen, higher sulfur tends to give you lower silicon and oxygen, et cetera. And while we didn't explicitly include hydrogen in our model, other studies have looked at this. It's a bit more controversial and has larger uncertainties on its partitioning. But just to get some numbers from previous studies, Tagawa et al. 2021, based on their metal silicate partitioning, estimated something like 3,000 to 6,000 ppm hydrogen in the core. And this is perhaps an upper bound. A number of other studies have argued for less, but that's perhaps the latest estimate we have on how much hydrogen you could get into the core from core formation. Okay, so I will end by just sort of summarizing all of the kinds of constraints I just threw at you. From cosmochemistry, geochemistry, consideration of the bulk composition of the Earth and what might be hidden in the core, suggests that the core could contain weight percent levels of silicon, something like 1.5 to 3 weight percent sulfur. From mineral physics, looking at the density and velocity structure of the Earth's core from seismology, we can do experiments and calculations to quantify the abundances of various light elements that would be needed to match the density or velocity, which are listed here for silicon, oxygen, sulfur, carbon, and hydrogen. Effectively, they're upper bounds on their abundances in the core, because if you had more than this, the core wouldn't be dense enough. But this is sort of a non-unique solution, because we know there's going to be a combination of light elements, so you're going to need less of all of them. Looking at phase relations of the core alloy, the fact that we crystallize an iron-rich inner core tells us we're on the iron-rich side of the eutectic, and that likely means we need a non-trivial amount of oxygen in the core. And trying to match the density contrast at the inner core boundary, it's likely that the core will have to contain some oxygen and or carbon, and also some silicon, sulfur, and or hydrogen to get the right sort of partitioning of the light elements between the inner and outer core to match the seismically determined density. From consideration of core formation and metal silicate partitioning, These are the sort of full ranges we could possibly achieve for these light elements, independent of other constraints. Again, not all combinations of light elements within these ranges are possible. But what we see in general is that core formation tends to put approximately weight percent levels of both silicon and oxygen into the core. But we can get quite a wide range of silicon to oxygen ratios in the core. You can get up to a few weight percent sulfur in the core, much less carbon. So carbon's probably not going to contribute too significantly to things like the density and velocity, but that amount of carbon does account for something like 80 or 90% of the Earth's carbon budget. So from that perspective, it's a really important amount to consider. And I will end there. Thank you very much for listening, and I'm happy to take any questions you might have.
Okay, thank you, Rebecca. It's a very nice talk. And yeah, if you have any question, then raise your hand. And I have seen. Okay, so first, Vasily, you can talk. You are allowed to talk.
Thank you. Hi, Rebecca. Fantastic talk as always. I'm excited to read the chapter in detail. I just wanted to ask about, there's a lot of discussion about basal magma oceans these days and possible re-equilibration between the evolving composition of the BMO and the core. I just wanted to know kind of how are you thinking about that? Is that to some extent captured in the models you were showing us? How might that modify your conclusions and things like that?
Yeah, that's a great question, and that's something I completely ignored in this talk today. Um, yeah, if there was like we always assume that the outer core is not reacting with the solid lower mantle because it would just be too slow in the solid. But if there was a basal magma ocean, and it was molten silicate in contact with molten metal, they should be reacting. Um, what we can say is that the core and mantle did not equilibrate at 136 GPa. If they did, there would be so much light element in the core, like it would be way less dense than it is now. Um, but I'm not sure we can rule out like a small amount of equilibration over a shorter time or something, or having this occur sort of sporadically during the Earth's formation. I think that would be a really interesting thing to look at as we get more data at higher pressures. But that's not something I've tried to look at yet.
Thanks so much.
All right. Then, okay, Malcolm, you can speak.
Thank you. Really nice talk. Thanks for that. I had a question. I'm not sure if there's an answer or not, but if I consider sort of from the mineral physics perspective, these relatively low weight percent light elements inside iron, at the atomic level, how are they incorporated? Is it best to view them as sort of inclusions of carbides or sulfur compounds within a matrix of pure iron? Or are these light elements incorporated inside the lattice of the iron as interstitials or potentially substituting as iron atoms on the iron lattice? Is there sort of a general way that is correct to view them, or are they all different, or is it maybe not known?
So if we're thinking about like a solid alloy like we might have in the inner core, um, I guess the short answer is it depends on the element and the phase. Um, for
Okay.
example, I think silicon is thought to be mostly like substitutional, like just taking the place of iron in the lattice. But a lot of these other elements, I think, are more in interstitial sites.
That would
Um,
make sense for hydrogen, for example. Yeah.
yeah, I'm not sure exactly how well that's understood for all of these elements at these kinds of pressures in particular. But people have looked at that a little bit. Yeah.
Okay, thanks. Interesting.
Okay, so there are also several questions via the Q&A, and maybe I can pick just one or two. And a question from RPG. So I'll read the question. Is there a is there a time integrated factor that has potentially changed the composition of core in terms of light elements? Maybe due to the possible interchange of elements at the core mantle boundary or over the time period of core mantle boundary evolution. Uh, do you have any answer, Rebecca?
Yeah, so there is going to be well, there's a few factors that people have identified that can change the composition sort of over time. I mean, even just crystallizing the inner core, you're going to slightly change the outer core and certainly the inner core. As Vasilia, I think it was asked earlier, if you have like a basal magma ocean at some point, that can continue reacting with the core. People have also been thinking a lot lately about things like exsolution from the core, that some light elements, especially with things like magnesium, but also perhaps like SiO2, some of these elements might have gone into the core at higher abundances than they would be happy staying at as the Earth cools off, and they might come out, like precipitate out and sort of build up at the core mantle boundary. So there's a lot of people thinking about this kind of thing, and there's a lot of ideas out there. I haven't taken those kinds of effects into account here, but there's certainly ways that it could maybe change. But I think those are a lot of those are relatively new ideas that I think we're still trying to understand exactly under what conditions they might take place and to what extent and how that would change the composition over time.
Okay, so I'll read one more question from the Q&A, and Steve can ask question. The question from Kirsten, how does the existence of the iron phosphorus phase in meteorite affect the consideration of phosphorus in the core?
Um,
Yeah.
yeah. So there's been some work on iron phosphides because of that, because we see iron phosphides in meteorites. And I guess, as I said at the beginning, like every element's in the core. It's just a question of abundance. But I think some of the more recent work on the volatile depletion trend of the Earth and also on the partitioning of phosphorus, I think it's probably not as abundant as at least things like silicon, oxygen, sulfur. But there could certainly be a non-negligible amount down there. And again, even if it's not an important contribution to the density or something, that could be an important contribution to the Earth's phosphorus budget.
Okay, let's say Professor Steve Dish, do you want to speak?
Yes, thanks. Can you hear me?
Yeah.
Yeah, great. Rebecca, this was a really lucid and comprehensive talk, and I really learned a lot. I really appreciate it. Thank you. I, um, as an astrophysicist, I've been favoring planet formation by pebble accretion. I know it's debated for the Earth, but also from a geophysical standpoint, you've got hydrogen, helium, neon in the Earth that I think could only have gotten there by having a magma ocean in contact with solar nebula. So I've imagined the Earth's core to be the merger of two cores formed very rapidly from proto-Earth and Theia, with the hafnium tungsten system reset at the giant impact of 60 million years. I'm wondering what you think are the greatest challenges from a light element perspective to those sorts of models.
Yeah, that's a great question. Of course, there's a lot of lines of evidence for pebble accretion that make it very attractive. Um, I think the biggest issue with the Earth, in my opinion, is the hafnium tungsten. I know people have proposed doing making two half Earths out of pebbles and then colliding them later so that you get the right timescale for the hafnium tungsten system. But the issue is that if you like fully re-equilibrate the entire mantle and core at some later time to reset the hafnium tungsten system, you're going to reset everything. And you're going to come out looking not like the Earth in the end. I'm not sure if anyone has sort of played around with like the parameters there, if you could make like multiple little Earths and collide them, and like maybe there's a way to get the hafnium tungsten right without screwing up other aspects of the chemistry. But it's going to be a little complicated because of that, and these sort of timing constraints we have on the process of core formation.
Thank you. Thank you.
Okay, thank you. It's already 1 p.m. So maybe last question, maybe from the. Okay, so maybe last question from the maybe Q&A. From the Justin Bank, is it possible that there is some heterogeneity in the inner core? Could that account for some of the difference in the measurement of the density difference at the inner core boundary?
Is it possible there's a heterogeneity in the inner core? I'm just going to say yes. I'm not sure if we would be able to tell. Yeah, I think maybe it's possible. I'm not sure how much that would affect the density contrast though, because these kinds of studies I think are it's sort of like a 1D average in those particular studies. So it would probably be sort of averaging out any heterogeneities that could be there. But that could be interesting to understanding things like how the inner core is growing and this process of cooling and crystallization and how it affects composition.
Oh, sorry. Now it's time. It's already 1:04 and the time is up. So that thank you everybody for coming to this Zoom talk, and thank you Rebecca for sharing time with us.
Thank you.
Thank you.